Hey y'all, in today's video, we're gonna look at rates of chemical reactions over time. In order to do this, remember the rates of chemical reactions can be studied using either changes in how fast the reactants are being used or the products are being created. So when we're looking at rates of reactions, we can measure either or both and get the same answer in the end. In general, we're using concentrations of reactants over time because most of the situations we're going to be in are going to utilize either the aqueous solutions or gases as our reactants. But understand that reaction rates, as we're discussing it, are going to be predicated on how fast those are changing over time. So if we look at data right off the bat, we could either see it in table form or in graph form. So here I'm showing table-based data and graphically based data at the same time next to each other. Now in the data I'm showing, we see the change in the concentration of butyl chloride, that's my reactant, and it's turning into butanol and hydrochloric acid. Okay, so my butyl chloride is reacting with water and it's creating butanol and hydrochloric acid. So if we look at the time series, you can see that the time is increasing down the table and the concentration of butyl chloride is decreasing as the time is increasing. Just so you know, the brackets around the butyl chloride there represent molarity, represent concentration. So if you ever see brackets, just understand that that's just signifying that it is a concentration value. Now, the evidence that I know it's a reactant in this process is the fact that it's being used. Remember, reactants are being used as time goes on. So the fact that the concentration of butyl chloride is dropping across time tells me that this is in fact a reactant. But that's not all that's happening. It's not just going down over time. Let's take a quick look at how the actual change in butyl chloride is occurring as time goes on. What I'm doing here is actually calculating the rate of change. Essentially, it's rise over run. It has gone down by a certain concentration over a certain amount of time. So we're going to show change using the delta, the triangle. Okay. So delta concentration divided by delta time represents the rate of change of my butyl chloride. Take a look. Now my rate of change of butyl chloride starts out at negative 1.9 times 10 to the negative fourth moles per liter per second. But by the end of the reaction, the rate of change is negative 0.56 times 10 to the negative fourth moles per liter per second. So as time went on, not only did the concentration get less, but the rate of change of the concentration got less. This tells me the reaction slowed down. Why is that? Why would the reaction slow down over time? Well, remember our last video. One of the things that affects rates is concentration. So as time went on and the concentration got less and less, the relative frequency with which collisions of reactants would occur also became less and less. So the rate slowed down. But here's the thing. Each of the rates that I calculated were over the span of 50 seconds or 100 seconds. And that's helpful to some extent. But if I'm driving a car from here back to my house, and my average speed is 20 miles an hour, that's not going to be a great argument for a police officer that might pull me over because I'm going 20 miles an hour over the speed limit. That's weird. How could my rate of speed be 20 miles an hour over the speed limit if my average speed was only 20? Well, maybe that's because I was going through a 25 mile an hour zone at 45 miles an hour, but that was only one moment across the entirety of my trip. See, there's a big difference between average rate and instantaneous rate. Average rate won't get you a ticket or get you out of one, but instantaneous rate will. So when we're looking at instantaneous rate of a chemical reaction, it's the rate at any one instant. There's no good way to calculate that without a little bit of calculus. But we can think about it on a graph. So here's what we're going to do. At any point of the curve, there is a line tangent to that curve. That line represents the slope, or at least the slope of that line represents the instantaneous rate of the reaction in that one moment. So the place at which that line is tangent to the curve, that time, the slope of that line is the rate of the reaction. A couple things to keep in mind. First of all, rates of reactions are only ever positive. We only think of reactions as going in one direction, and they're always going positive in that direction. It's like my car. Doesn't matter which direction I'm driving my car, either going forward or backwards, I think about my speed as always a positive. Okay? So when we're looking at rates of reactions, we're looking at positive values. Even though the reactant is being used, the rate of the reaction is positive. Okay? So that's the first thing. So if we look at the slopes of the lines tangent to the curve at two different places, we can now clearly see that the rate of the reaction has slowed down over time. At the first moment, time equals 0. The line tangent to the curve is known as the instantaneous initial rate, or oftentimes we'll just call it the initial rate. So if I say initial rate, understand that that is the instantaneous rate at time equals 0. Remember though, I can't measure anything in 0 seconds. So what we do as scientists is do not measure the instantaneous rate in an instant. We actually just measure it over a very short period of time after time equals 0, and we call that our instantaneous rate. It's not a perfect system, but it's a pretty darn good system because the rate of the reaction immediately after the start isn't all that different from at time equals 0. So we're basically interpolating backwards to time equals 0 from a very short window after the reactions begin. So that wraps up today's video. Today we talked about the rates of chemical reactions being measured via tables or graphs. Remember, when we're looking at graphs, the graph itself can be used in kind of a bigger picture understanding of rates over time, but more important are the lines tangent to the curve at any instant, because that's what's going to give us instantaneous rates of chemical reactions. When we get a little bit later into the unit, we're going to actually talk about how to calculate instantaneous rates of reactions, even without a graph in front of us. The other thing to understand is that tables are going to be really helpful for tracking the changes in concentration over time. And many times using laboratory data, we're going to actually take these tables and create lines of best fit in order to be able to create and understand instantaneous rates at any given time. Finally, we defined instantaneous rate and initial rate, which is the instantaneous rate at time equals 0. So that's it for this video. I hope you enjoyed it, and I'll see you in the next one.